I had my chain snapped once.
Oh, that's...
And, well, snapped, it came apart, and...
You slapped your leg?
No, I was like I was trying to go up a hill, and as I put force into the pedal, it broke, and I went over, and I still have the scar on my hand from that. It's a little road rash. Okay, how are y'all doing? Good? Okay, I offered a question, right? The inventory control problem, and that was a bonus, right?
Yes,
So if you have that, I'll take that now.
That's problem 8, correct?
Yep. Okay. Anybody else? Got it? Okay. Anyone else? Bonus question? Okay. There you go. Thank you. Did you do the bonus or no?
Yes.
Yes? Okay. Thank you. Okay, I'm not going to accept this late, so it's now or never. Okay, thank you. Anyone else? All righty. Okay, we are continuing chapter 13, section 1, antiderivatives. All right, so the one thing that we established last class was this thing called the power rule. And we also introduced this new notation. Remember this symbol right here? Along with that, that tells you that you want to take the antiderivative, right? To find the antiderivative of a function. And I told you to kind of ignore this dx for now, right? It's going to come into play today, though, all right? But this tells us we want to find the antiderivative of x to the n, and then here's the formula that we had. So long as n was not -1, and if n was -1, then this is what happens. So we did that last class, and we need to kind of wrap up a couple of things in this section. So I want to give us one more little recap of last class. That when we were finding the antiderivative, let's say for a specific example, I said find the antiderivative of x squared. Then if we use the power rule, what would the antiderivative of this be? 1/3 x to the third power, and then we say plus c, right? Okay, that's our antiderivative. Now the plus c was because we could plug any number in here. Both plus and minus, and that would give us all of the different things we could think of. Like let's just come up with something. 1/3 x cubed plus 1 would work. 1/3 x cubed minus 1 would work. 1/3 x cubed plus 4. 1/3 x cubed minus 4. And I tried to explain that there's an infinite number of answers, but they all look like something. They all look like 1/3 x cubed, and then they've just been moved up and down, right? Yes? So we all understand that this gives you like a family of answers, right? Doesn't give you one of these specifically, gives you the entire collection of them. So now what we're going to do is we're going to try and add one more layer to the problem that's going to allow us to find a specific answer. So let's start with this one. Let's say that I tell you that the derivative of, that's supposed to be a derivative mark. Let's say I tell you that the derivative of some function is 600 minus 0.6x, and then I tell you and r of 0 equals 0. And I ask you to find r of x. All right, so let's first try and understand what's going on here. I'm giving you the derivative of a function, right? So this is different than in the past. In the past, I've given you a function, asked you to find its derivative. Now I'm giving you the derivative, and then I'm telling you that the function r, when you plug 0 in, it spits out 0. So notice that I'm giving you information about the function r, and I'm giving you information about the derivative of r, right? And then I'm asking you for the r function. Like, what is the r function? So how can we go from the derivative back to here? Right? So like if I gave you r, I said take derivative, you should get that, right? I want to go backwards. So how do we go backwards? Antiderivative, right? We're going to take the antiderivative. So let's take this, look at this. R of x should be the antiderivative of this. Now let's see if that makes sense. We're given the derivative function. We want to go backwards, so we take the antiderivative of it. And that should give us back r before we took the derivative. I know it's weird, but it's kind of like we're unwashing a clean car. Okay? So we got a clean car, it's gone through the car wash. We want to go backwards to what it was before. So let's just find the antiderivative of the r prime, which is 600 minus 0.6x, and then dx. We always have to put that dx here. It always has to be at the end of our integral. I think you should, because this is two terms, right? Separated by subtraction. So I like to put it in parentheses. I mean, you could get away with it without, but it doesn't hurt to just throw them in there. Okay, so now let's do this. We're going to do these separately. So we can find the antiderivative of this one, and then the antiderivative of that one. So I already heard what the antiderivative of 600 was. 600x. And we did that towards the end of class last time. The antiderivative of a constant is just the constant times x. So, oops, I forgot to put the x.
Would the other one be negative 0.3x to the second?
Yes. So how are we doing that? You're correct, but how are we going to do this piece? So what I would suggest you do is, this is a number, right? That's sitting in front of x. So I'm going to write down the number, and then I'm going to find the antiderivative, so times, take the antiderivative of x. And remember, that's x to the first power. So the power rule would tell us that the antiderivative of x to the first power is 1 over 2 x squared, using the power rule. Yes or no?
Yes.
No?
Yeah, I'm like sneezing out.
Okay, but yes? 1/2 x squared, like that. Now, plus c. Now don't forget you have to have the plus c here, right?
So, sorry, we got the 1/2 fraction.
I'm using the formula 1 over n plus 1, x to the n plus 1. I'm using the formula from last class.
Oh, okay.
Right? So for us, if we're trying to find the antiderivative of x to the 1, then n is 1. So I'm just going to go 1 over 1 plus 1, x to the 1 plus 1. That would give me 1/2 x squared. Okay? So now where are we? This is equal to 600x minus, now, if you multiply, you can get your calculator or just do it mentally. This times, or this divided by 2 would give you the negative 0.3 x squared, and then plus c. Is that all right? Now, right now, this is what we have. This is what we think our function is, right? But here's the problem. This r of x function that we have is a family of functions. It's actually a bunch of them, isn't it? So we have not exactly nailed down the exact function. But there's one piece of information we haven't used. We haven't used that information, have we? What that tells us is that when we plug 0 into this function, it should spit out. You know what? Let's change this. Can we change this? Kind of boring. Let's change it to like 4, okay? It's just more interesting that way. So that tells us when we plug in 0, we should get 4, okay? So if I go over here and I plug in 0, let's see what happens. This becomes what? 0. And then minus, if I plug in 0 squared, that's 0. That's 0. And then that's plus c. Now I'm not replacing c, right? I'm replacing x with 0. So the c is still c, right? Does that make sense?
Yeah.
But this has to be equal to 4. And that means that c has to be 4.
Okay, that's fine.
So c has to be 4. So now I'm ready to go ahead and give my final answer, which is what that r function is. But now I know this c, right? Now I know the actual value of c. 600x minus 0.3x squared plus 4. This is it. So the main point here is this. If I give you the derivative of a function, you should always be able to go back and give me the antiderivative to get to this, right? You'll always be off by c. You'll always not know what that is, unless somebody gives you some more information. They give you more information, then you can actually go and recover that c. This piece of information is commonly referred to as an initial condition. An initial condition. Because it's giving you something, some condition that the function has to have in order for it to be the one you're looking for. So using that initial condition, we can actually recover c. All right? Okay. So if you ever want to check your answer to see if you got it right, you can do two things. First thing, plug in 0, and you better get 4, which we would get. And then take the derivative of that. If you take derivative of this, you would get 600, right? And then you bring the 2 down, multiply, you get negative 0.6x, which would be this. So if those two check off, you've got it. Okay? Now I'm going to give you another one, but I'm going to give you the same sort of thing with some slightly different notation. So how about this? How about if I tell you that dy dx is equal to 3x squared minus 2x plus 1. Yeah. And let me tell you that y of 1 equals 6. I want us to find y of x. Do you all see that this is the exact same problem?
Yeah.
You sure? Everyone see that? I'm giving you the derivative of something, right? I'm asking you to find the y without the derivative. This is kind of like, look at this as being like f of x, okay? So this is like, I'm asking you for the function, and then here's its derivative. Make sense?
Yeah.
Now, what is this right here?
That's the
That's your initial condition. That's saying once we get back to here, when we plug 1 in for x, this thing better spit out 6, all right? And that will help us get our c that we're looking for. All right, so where should we start? Find the antiderivative, right? So if I want to know what y of x is, what I need to do is take the antiderivative of this, right? Okay, so what is the antiderivative of that right there? because we're going to do these separately, right?
So that one?
Yeah.
X cubed minus x squared.
Okay, so you're saying the antiderivative of that's x cubed? Yeah, so there's different ways of looking at this, and this is just going to depend on how you feel about it. What I've told you is that if you have a constant in front, like the 3, you can just ignore it. And then, and then it can be the antiderivative of x squared, which would be 1/3 x cubed, using the formula, 1 over n plus 1, x to the n plus 1. That was your homework, right, to do that? So I'm assuming you're kind of familiar with that. So 1/3 x cubed, that's what that is, right? But I have a 3 in front of it. So it's really 3 times 1/3 x cubed, and then the 3's are going to cancel, and you're just going to get x cubed. Is that all right? Then I have minus 2, that's this one, and now I take the antiderivative of x, which is 1/2 x squared. Okay, guess you're coming with me. 1/2 x squared, and then finally, have you ever done that where you're like washing your car and then you drop it, and then you drop the handle, you drop the spray hose and it hits the handle and sprays back at you? No?
Yep.
Am I the only one that's ever happened to?
No, never tried.
Hey, you never drop.
That one was plastic, no.
What's the antiderivative of 1? Oh, that's a derivative. What's the antiderivative of 1? 1x, or just x, right? Because what you always have to ask yourself, like, what do you take the derivative of to get 1? Just x, right? What if this was a 4? What would our antiderivative be? 4x, right? If this was 10, it would be 10x. So this is going to be just 1x, or just x. And that's it? We're done? Plus c. Plus c. Don't forget the plus c, right? We called that, last class, we called that the constant of integration, is what I labeled it as. But let's clean this up. We said the 3's canceled. That was x cubed. 2's actually cancel there, so we get minus x squared. Then we get plus x and plus c. So far, here's what I think y of x is. So I've got a family of functions, right? I've got a family of functions because of the plus c. Now let's actually find the particular one we're looking at. So let's use this information, right? When we plug 1 in, let's see what happens when we plug in 1. We're plugging 1 in for x. So we get 1 cubed, right? Minus 1 squared, plus 1, plus c. But what must that equal? 6. All right, so what do we get here? 1 cubed is 1, right? 1 squared is 1. So those are going to cancel each other out. So you get 1 plus c is 6. And if you subtract 1 from each side, you get c is 5. Now be careful. Your answer is not c equals 5, right? That's not your answer. What is your answer? It's all of this again, but replace c with 5, right? So your answer is y of x equals x cubed plus x, minus x squared. Minus x squared plus x plus 5, and box it up. Feel all right about that? I'm going to give you a problem, a word problem, and then I'm going to let you all work on it. And I haven't done a word problem yet, but I want to see if y'all can put this all together and use it for something. Okay, here we go. the rate of monthly sales of a new football game I guess we can just say that these are like video games or something. Yeah, like Madden or whatever. Newly released football game is given by S for sales. S prime of t equals 500 t to the 1/4 power. Here, t is number of months, and S of t is total games sold after t months. Here's the question. When will monthly sales reach 20,000 games? Now I'm going to help you. I'm not just going to throw this at you without at least helping you figure out what you need to do. You ready to talk about this? Okay. The rate. When we see the word rate in a word problem, we should be thinking derivative. Okay? The rate of monthly sales of a new football game is given to you by S prime of t. So this is a derivative, right? Derivative is a rate. So they're giving, this is the rate at which we're selling games, is equal to 500 times t to the 1/4 power. T is the number of months that have elapsed. Maybe I should put that. Number of months, let's add to this, since the release, okay? Since we released the game. So since release. So t is the number of months that have gone by since we've released the game. So after 1 month, t would be 1. After 2 months, 2, so on and so forth. S of t. Now, this is S prime of t, right? S of t is the total games sold after t months have gone by. When will the monthly sales reach 20,000 games? Can anybody ask me? Can anybody tell me what this question is asking you for in terms of the functions?
How long will it take to reach 20,000?
Okay, how long will it take? So how many months, right? So they're asking for a t, right? They're asking for a t. They're saying, at what t will what be what?
At what t will the game, will the 20,000? Will S equal 20,000?
Will S equal 20,000, right? Not S prime. See, S of t, not with the derivative, that's the rate of change. This is how many games you've sold, right? S of t gives you how many games you've sold after t months. Yes? This is asking you at what value of t, so when are your total sales going to be 20,000? So this question is asking you, when will S of t equal 20,000? That's the question. Okay, so maybe we can work through this one together, unless y'all feel like y'all can get it. What do you mean? Okay, so we can go from the prime, we can take this backwards, can't we? And we can take it back to S of t. Y'all want to do that? Go ahead, see if you can do it. I'll give you a minute to use your formulas to take S prime back to S. In other words, give me the antiderivative. And don't freak out. We're using t instead of x, right? So this is dt instead of dx. See if you can figure that out first. I'll put the formula over here just in case. What's n in the problem? What's the n? 1/4. So you're going to have to do some fraction stuff here, aren't you? You can do a decimal if you really want to. That's okay. You'll need your calculator though, right? Show me your hand up whenever you've got the antiderivative, okay? I just want to get a feel for how long it's taking everyone to get that. You think you do? Let me see. Hold on, I have to do it in my head here. Okay. Okay, so what about the 500 that was out there? I think that's the only thing you're missing. Yeah, don't forget the 500. That'll just come for the ride. Okay, so what you've done so far looks okay. All right. You think you got it? Okay. 400?
I don't know. Where did I go wrong?
Okay, so 5. So what goes out front? What did you put out front?
I dropped both. I dropped 5 down there instead of.
I think you're going.
All right.
It's a little bit tougher when you have fractions because look at what you're doing here. Like if this is 1/4, right? If that's 1/4, then this is 1/4 plus 1. Okay, so you got 5/4 there.
Yeah.
But out here, this is going to be 1 over 1/4 plus 1 is 5/4, right? So you have 1 over 5/4,
Yeah.
which flips over and becomes 4/5.
Okay. So I was somewhere in the right.
You're in the right. Yeah, it's. I couldn't tell where you got the 100 from, but. Oh, you did like 1/5 out there or something. Okay, you're just missing the 4. Yep, you're good. Yep, that's it.
Yeah.
Yep. Get rid of the dt. dt is not. It goes away. Yep. You just have the plus c though.
Do I keep the 500 and I just bring it with it and then put the 1 over?
Yep. Yep. Anyone else think they have it so I can check to see? I'm going to start writing it out. That's me using the formula exactly the way it's written on the board with just x's and t's instead of x's. Does anyone have a question on where this came from? This went away and the dt goes away because we're taking the antiderivative. 500 comes down, n is 1/4, so I do 1 over n plus 1 x, but we're using t to the n plus 1. Plus c. Now, just to show of hands, how many of you you think you're just going to go to decimals on this? Calculator? Is that most of you or no? Yeah, probably? Okay, then you're going to need to put this in your calculator. That's going to be 1.25. And then take 1 and divide it by 1.25. And you should get 0.8, right? So this all here should turn out to be 0.8. And then this up here should turn out to be 1.25. So here's where we should be. We should have 500 times 0.8 t to the 1.25 plus c. So this part here, all of it together, is 0.8. And we still have to multiply that times 500. And that's where we're going to get 400 from. So we get 400 t to the 1.25 plus c. Questions on that? You good? You good? So I'm going to write down right here where we are. We have what we think our function is, our s of t function, is 400 t to the 1.25 plus c. That's where we think we are, right? We already know from the previous examples that we're off by a bunch because we don't know what c is, right? We don't know what c is. So how are we going to, see, what we want to know is, we want to know when this is 20,000, right? I'd like to know when this is equal to 20,000. But the problem is I don't know what c is. So this is kind of the stretch here. How are you going to figure out what c is? Have I given you an initial condition? Is this an initial condition, though? No, that's not telling me. For an initial condition, I would have to tell you at a certain month you had this much sale, or this much sales. This is saying when is your sales 20,000? But if you just think about the problem itself, you actually do know your sales at a certain point in time. At 0, you should have 0 sales, right? That's not given to you in the word problem, but you have to deduce that, right? At 0 months, you haven't released the game. So you should have no sales, right? So my initial condition although not stated in the problem, is that s of 0 equals 0. At 0 months, I should have 0 sales. And now what you can do is you can plug 0 into the function, right? We're going to just use that function. S of 0 must be 400 times 0 to the 1.25, that's not going to matter, plus c. But what must that equal? 0, right? So when you plug 0 in for t, it should spit out 0. So just be sure you understand that this 0 was the one that got plugged in, and this 0 is the one that comes out. So all of this gets killed off, right? That's all gone? So c must be 0. C must be 0, right? If that's all that's left, c is 0. And if c is 0, then this function actually just simplifies really nice to become s of t is equal to 400t raised to the 1.25. That's it, right? Because c is 0. Right? Plus what? Well, we said c was 0, so this is it. This is our sales function. That is it right there. Well, what's 0 raised to any power?
Okay.
Right? 0 and then times 400 is still 0.
Oh, no, I was wondering for that, so it just makes, that's what I was wondering. I was like, something.
Have we answered the question yet?
No.
No. Now what? This is the formula for s of t, and we want to know when that s of t is 20,000. Set that equal to 20,000. Don't plug 20,000 in. There's a difference. We want to know when that is 20,000. So our final computation that needs to be done here is that we have to take 400 t to the 1.25 must equal 20,000. There we go. So how should I solve that? What should I do first? Divide both sides by 400. So what happens if you divide both sides by 400? What do you get? 50? Everyone agree with that? Now we have something difficult because we used decimals, right? Which a lot of you wanted to use, and that's fine. But you've got to figure out a way to get t right now. So how do you get t? Because right now we have t to the 1.25. So let me help you with this by just looking over here and looking at something. If I said t squared was 50, how would you solve that? You would take the square root on your calculator, wouldn't you? Right? That's what you would do? So if you did square root on your calculator, technically what you're really doing is you're taking t squared and raising it to what power? What does square root really mean? Raise it to what power? 1/2. And the reason we're using 1/2 is because 1/2 and 2 kill each other off, cancel each other off. All right? Agreed? You understand this? So what I need to do here is I need to take t to the 1.25. I need to raise it to the 1 over what? Like if it was t squared and we want to get rid of squared, we raise it to the 1 over 2, right? Here, to get rid of that, we need to raise it to the 1 over 1.25. Right? If you're using fractions, that's what you would do. But I just said everyone seems to want to use decimals, so this is the way I'm going to do it. Whatever you do to one side, you have to do to the other, right? So it's like when you square rooted both sides. Here we're doing this weird thing on both sides. Now, what do we know the left side's going to become? Automatically, what does this become? T. Okay, so that's t. We're not worried about that. But that we need to actually figure out how to do this on our calculator. So what I want you to do is first figure out what this is. What's 1 over 1.25? It's 0.8. Okay? Everyone good with that? That's 0.8. So we really need to do 50 raised to the 0.8. And 22.86? Wait, say again? 22.87. 2.8786, whatever, close enough. Now, if you have your calculator and you're having trouble getting this, let me know and I can try and help you figure out what keys to press. You're good? Okay. Everyone else good? So this is what t needs to be. So what can we say? I mean, that's an answer, but that's a decimal, right? Roughly speaking, when should we expect our sales to reach 20,000 games? About 23 months in. Okay, almost 2 years into the game release, we should expect sales to be about 20,000. Okay? So this problem was, there's some little details in here, but the fundamental principle is the same. Started out with the derivative, found the antiderivative plus c. Had to use an initial condition to figure out what c is. And then we used that information to be able to figure out when the sales were 20,000. And we could really ask ourselves, when are the sales going to be 500? When are the sales going to be 1,000? All we would do is just take our master formula right here and set it equal to whatever number you're interested in. And that'll tell you how long you have to wait before your sales get that high. All right? Okay. So you can now pretty much attack the rest of the homework for 13.1. And we're going to start 13.2. Now I was looking at the calendar, and on our calendar we actually skip 13.2 and save it for later, but I'm going to do 13.2 right now. So I'm kind of changing the calendar a little bit in our order of doing things. All right, 13.2. Integrating, or I'll say integration by substitution. Now, to get this started, I want to remind you of something, because I know it's been a while. If y is equal to, let's say, 3x squared plus 1 to the 7th power, and I ask you to find y prime, let's see who remembers how to do that. How do I take the derivative of that? Use the power rule with chain rule, right? It's the chain rule also. So you would say, okay, I've got something to the 7th power, right? So 7 would come out first. And then what? The same thing. You don't touch it, right? You just leave this alone. 3x squared plus 1 to what power?
Times the derivative of the 3x squared plus 1.
I will do that, but to what power do I? Okay, so this is the 6th power. So the power comes down by 1. That's basically, that's like your power rule. And then now you say, the chain rule said, then you take the derivative of what was in here. And that's just 6x. Does that look familiar to you all? This would be 42x, right? And then 3x squared plus 1 to the 6th. Right? Any questions on that? Start with this, take the derivative, you get this. So what do you think I'm going to ask you now? How would I go backwards? Oops. How do I go backwards? See, this is the answer that we get when we take the derivative, right? How would I ever go from that back to this? You see the difficulty in it? I mean, that is not easy to see that the antiderivative of that is this. And we can't use the power rule. You know our little power rule we've just been using? We can't use it because we don't have like x to a power, like plus or minus x to a power plus or minus. We've got some multiplication in here. We've got raising exponents. So we can't do it one by one like we did before. It's very problematic. And so in general, taking antiderivatives is much more difficult than taking derivatives. Like doing this to this, much easier than going from here back. So how can we handle something like this? The technique we use is something called substitution. All right? Now, y'all are all looking at me like. What is substitution?
Do we do the integral last class?
Yes.
Okay, that's what I'm
Yep.
confused. Okay.
Yep. Yeah, we talked about antiderivatives and used the notation, so. All right, so what is this method of substitution? Do you see you see the difficulty, right? Like going from here back to this? I just want everyone to agree that this is not straightforward, right? There's something else going on here. All right, so what is this technique of substitution? Well, the thing is, it's not really a technique. It's something that you have to try, and you have to just kind of see if it works. So most of the time in math, we give you formulas, and then you just use the formula and just do it. But this is one of those things where you just have to kind of try something. So here's what I want you to do. I want you to see, can you find something in here and its derivative? What the hell is he talking about? All right. So let me see if I can explain what I mean by this. I am going to look at this, right? And I'm focusing all my attention on this right here. And I'm looking in there to see if my eyeballs can see something in there, and also next to it somewhere, its derivative. So for this first example, I want to point something out. Do y'all see this 3x squared plus 1? Okay? Y'all see that right there? What is the derivative of that? 6x.
Divided by 72 gives you 7.
So I'm trying to identify something, right? And I also need to see its derivative there too. So if I look at this as being my something, you just told me that the derivative of that was 6x?
Yep.
Do you see that I have a 6x right here?
Yep.
It's 7 times 6x, right? So I need to recognize that 42 can be written as 7 times 6x. So I have to recognize that. It's not, this is very different than anything we've done so far, right? So here's what I'm going to do. I'm going to rewrite the problem again. I'm going to write, just so you can see it, this is 7 times 6x times 3x squared plus 1 to the 6th power dx. Now, is that a little bit more obvious that I've got something and its derivative here? Yes? Okay. So here's what we're going to do. We're going to make a substitution. Here's the substitution that I'm going to use. Let u be equal to that something that I identified. So I'm going to replace in this problem this thing right here, right? I'm going to replace it with u. Is that okay with you? Right? I'm going to replace that with u. Now, if I replace this with u, then this is going to say u to the 6th, right? But then I'm going to have x's here. So I'm going to have x's and u's mixed together, right? I'm trying to get everything over from x's switched over to u's. All right? So here's what I'm going to do next. I'm going to take this equation and I'm going to take the derivative of it with respect to x. So this is just notation. If I say take derivative of this with respect to x, that's this. And the derivative of this with respect to x is this, right? 6x. Y'all still there?
So we put du, if we put du to dx equals 6, does that mean then we're getting?
Well, let's see what it does, okay? Let's see what it does. So I'm going to replace everything. I'm going to replace this with u, right? And I'm going to replace 6x with this.
Oh, man.
And watch what happens. This integral becomes 7, right? What's 6x being replaced with? Du over dx. What's that being replaced with? U to what power? 6th, and then I still have dx, don't I? You'll see that? Do y'all see that? You see the dx's cancel? So at the end of the day, what I have here is a 7, right? I'm going to write u to the 6th in front, u to the 6th, and then du. Do y'all agree with that? I just kind of changed the order of those. Okay? What's that equal to? So what can you do with this? What can you do with this? What rule can I use? What rule? If I'm saying, look, if I walked in today, say everyone take out a sheet of paper and take the antiderivative of that, that would have been just like a homework problem. Right? So what would the antiderivative of that have been? Seven times 1/7 x to the 7th plus c.
Oh, it's a, what's the power rule? What are you asking for? Exactly. So is that, we're calling it the power rule? It's the 1 and 1 and x1.
how about this one? 5x minus 3 to the 10th power dx. So do you see something in its derivative here? Five, what do you mean? The 5x minus 3, what's the derivative of that? 5. And you see a 5 there? Right? See it? So if we let u be equal to 5x plus 3, or minus 3, right? And then take its derivative, du dx. What's du dx? 5. Then we can rewrite the problem, can't we? So what would this new problem be? Hold on. Let me give you an opportunity. Rewrite the problem in terms of u. Okay, so where the 5 is, put du dx. Everyone follow that? That's going here. Okay, parenthesis. What do you got?
Or is it 5x or 5?
You're trying to replace this, right? I want it in terms of u. This right here is u, right? Right? So u to the what? To the 10th? And we're trying to replace dx, right? But we see that it's going to cancel here, right? So we can just leave that there the way it was from like the last problem. And you see that those dx's were going to cancel. So that was about, you did about, I'd say, 25% good on that one. I'm only calling you out because you're on your phone texting. It's the only reason I'm calling you out. So if you would have given me the entire answer, like no problem, I would have no problem with that. But if your attention's half there and half here, it's going to be difficult. So that was not bad. I was expecting worse. I mean, because I didn't think you were paying attention. Okay, so what happens now?
Now we gotta find the, I don't know the term, we gotta find the final result.
Let's rewrite it.
There you go.
How do we oh my gosh.
Well, what's the final term?
Just comic relief. You were saying, yeah, the power rule, and then she said rewrite it, and you're like, yeah. Okay, so what is that rewritten? U to the 10th, du, that's it? Right? So the dx is canceled, we got u to the 10th, du, and now what?
Plug them in, you plug in the original numbers.
Well, got to find the antiderivative first. Before you go, because look, if you plug, look, what happens if you plug this back in? If you plug this back in for u, and then du, so if you plug in now, you're going to go back to this. But you want to get the antiderivative first. So give me the antiderivative of u to the 10th. 1 over 11, u to the 11th, plus c, right? Just remember what direction you're going here, right? Antiderivative, not derivative. So antiderivative is going to be 1 over 11, u to the 11th, plus c. Now you replace your u with 5x minus 3 to the 11th plus c. There it is. Now, how do I know that that answer is right? What could I do to check it?
Plug in the fraction.
I just tried to find the antiderivative of this, right? I think the answer is this. To check it, I could take the derivative of this and see if I get that. So if I take the derivative of this, we have to see first the 11 would come out and then go away, wouldn't it? And then the power would come down by 1. So I would have 5x minus 3 to the 10th. That would be that, right? Then you have to take derivative of what's inside, and what's the derivative of what's inside? 5, and that would give you that. See, we're trying to undo the chain rule. It's very difficult to undo the chain rule.
How do you get dx back up there? That's when it doesn't really matter.
The dx is because, see, this is a great question, but it's difficult to explain. The dx comes from, you know how I said take the derivative in here, and I said we got 5? Okay, so let's just look at this. If I take derivative of what's in here, we all agree derivative of that's 0, right? Okay, derivative of this, I would like for you to just bring the 5 along for the ride, and then what's the derivative of x? You say 1 usually, right? But if I wrote dx instead of 1, this was like when we were doing implicit differentiation. This is like dx, kind of. And so that's where that comes from. It's really like a 1, okay? All right. We need to do another example. There's no such thing as too many examples on this. All right. You ready? Hoping the wheels aren't going to come off on this one.
Are you making one up, sir?
I'm making one up. 5x squared times e to the x cubed dx. Oh, man. Now this one's going to be a little bumpy, okay? So you're looking at that.